Download this code from codegive.com, link in the description below. OK, let's dive into the world of kernels, specifically in the context of CS480/680, and provide a detailed tutorial with code examples. We'll focus on understanding the concept of kernels, their significance in machine learning, especially with support vector machines, and practical implementations in Python with libraries like numpy and scikit-learn. CS480/680 Lecture 7, Kernels, a comprehensive guide. 1. Introduction. What are kernels? At their core, kernels are functions that compute the dot product between the images of two data points in some, potentially high-dimensional, feature space. This might sound abstract, so let's break it down. Asterisk feature space asterisk imagine you have data points in a low-dimensional space, example 2D coordinates. You might want to transform these points into a higher dimensional space where they become linearly separable. This higher dimensional space is the feature space. Asterisk mapping function, phi a function that maps the data points from the input space to the feature space, phi, x. For example, phi, x, equals, x0 caret 2, x1 caret 2, x0 asterisk x1, maps a 2D point x to a 3D space. Asterisk kernel function, k a kernel function k, x, y, calculates the dot product of the transformed data points without explicitly computing the transformation phi, x. Mathematically, k, x, y, equals phi, x, phi, y. Asterisk kernel trick asterisk the kernel trick is the magic of using kernel functions. Instead of explicitly computing the feature mapping phi, x, and then calculating the dot product, we use the kernel function k, x, y, directly. This is often much more computationally efficient, especially when the feature space is very high-dimensional or even infinite-dimensional. 2. Why use kernels? Asterisk linear separability asterisk many datasets are not linearly separable in their original input space. Kernels allow us to implicitly map data to higher dimensional spaces where linear separation becomes possible. Asterisk computational efficiency asterisk the kernel trick avoids explicit computation of feature mappings, saving time and memory. This is crucial when dealing with complex feature spaces. Asterisk flexibility asterisk kernels provide a framework to use different measures of similarity between data points. Different kernel functions can capture different types of relationships in the data. 3. Common kernel functions. Here's a breakdown of some widely used kernel functions. Asterisk linear kernel asterisk. Asterisk k, x, y, equals xy, simple dot product. Asterisk equivalent to performing linear classification in the original input space. Asterisk pros, fast to compute, easy to interpret. Asterisk cons, limited to linearly separable data. Asterisk polynomial kernel asterisk. Asterisk k, x, y, equals, xy plus c, caret d. Asterisk c is a constant, usually 0 or 1. Asterisk d is the degree of the polynomial. Asterisk maps data to a higher dimensional space where features are polynomial combinations of the original features. Asterisk pros, can model nonlinear relationships. Asterisk cons, can be computationally expensive, may lead to overfitting, especially with high degree D. Asterisk radial basis function, RBF, or Gaussian kernel asterisk. Asterisk k, x, y, equals exp, dash x, y caret 2 slash, 2 asterisk sigma caret 2. Asterisk x, y is the Euclidean distance between x and y. Asterisk sigma, sigma, is a hyperparameter that controls the width of the kernel. Sometimes, gamma equals 1/2 asterisk sigma caret 2 is used instead, so you might see exp gamma asterisk x y caret 2. Asterisk maps data to an infinite dimensional space. Asterisk pros, very flexible, can model complex nonlinear relationships. Asterisk cons, computationally more expensive than linear kernels, sensitive to the choice of sigma, or gamma, can be prone to overfitting. Asterisk sigmoid kernel asterisk. Asterisk k, x, y, equals 10, alpha asterisk, x, y, plus c. Asterisk alpha and c are hyperparameters. Asterisk resembles a neural network activation function. Sometimes used as a proxy for a neural network with a single hidden layer. Asterisk pros, can model some nonlinear relationships. Asterisk cons, can be unstable and not a true kernel, doesn't always satisfy Mercer's theorem. 4. Mercer's theorem and valid kernels. A function k, x, y, is a valid kernel if and only if it satisfies Mercer's theorem. This theorem states that the kernel matrix, a matrix where ki, j equals k, x underscore I, x underscore j, for all data points x underscore I and x underscore j in your data set, must be positive semi-definite, PSD. A PSD matrix has non-negative eigenvalues. In essence, Mercer's theorem ensures that the kernel corresponds to a valid dot product in some, possibly infinite dimensional, feature space. If a function doesn't satisfy Mercer's theorem, it might not lead to stable or meaningful results. 5. Implementing kernels in Python, with numpy and scikit-learn. Let's see how to implement kernels using Python libraries. Explanation of the code asterisk. 1. Data generation asterisk. We use make_classification from scikit-learn.datasets to generate a synthetic binary classification dataset. This allows us to easily test our kernels. 2. Data splitting asterisk. We split the data into training and testing sets using train_test_split. 3. Data scaling asterisk. Scaling the data using standard scaler is crucial, especially for kernels like RBF, as it prevents features with larger ranges from dominating the distance calculations. 4. Kernel functions asterisk. We define 3 common kernel functions: linear_kernel, polynomial_kernel, and RBF_kernel using numpy for numerical operations. 5. Custom kernel classifier asterisk. We make a custom classifier to demonstrate training from scratch. This is for academic illustration and understanding. This simplifies the core logic. The fit method constructs the kernel matrix by computing the kernel function for all pairs of training points. It uses scikit-learn's SVC to train on the pre-computed matrix. The predict method then uses the kernel to classify new data points based on their similarity to the support vectors. 6. Using scikit-learn's svm.svc We use svm.svc, support vector classification, from scikit-learn to demonstrate how to use the built-in kernels. This is the recommended approach in practice. We create SVC objects with different kernel types: linear, poly, RBF, sigmoid. We fit the models to the training data and make predictions on the test data. We calculate the accuracy using accuracy_score. 7. Pre-computed kernel We define a function precompute_kernel to calculate the kernel matrix beforehand. This can be useful if you want to use a custom kernel that's not directly supported by scikit-learn, or if you want to optimize the kernel computation. We pass precomputed as the kernel argument to svm.svc. Key points to remember: Hyperparameter tuning. The performance of kernels is highly dependent on the choice of hyperparameters, example degree for polynomial, gamma for RBF, cof0 for polynomial and sigmoid. Use techniques like cross-validation to find the optimal hyperparameters for your data. Data scaling. Scaling the data is essential for many kernels, especially RBF. Computational cost. Kernel methods can be computationally expensive, especially for large data sets. Consider using techniques like kernel approximation or feature mapping to reduce the computational burden. Interpretability. Linear kernels are generally more interpretable than nonlinear kernels. It can be difficult to understand the decision boundaries learned by complex kernels. Choosing the right kernel. There's no one-size-fits-all kernel. The choice of kernel depends on the characteristics of your data and the problem you're trying to solve. Experiment with different kernels and compare their performance using cross-validation. Advanced topics, beyond the scope of this tutorial, but important to know. Kernel approximation. Techniques like random kitchen sinks or Nystrom methods to approximate kernel functions, reducing computational complexity. Multiple kernel learning, MKL, combining multiple kernels to leverage different types of information in the data. Kernel alignment. Techniques to choose kernels that are well aligned with the data. Regularization. Regularization techniques, example L1 or L2 regularization, to prevent overfitting, especially when using complex kernels. This tutorial provides a solid foundation for understanding kernels in the context of CS 480/680. Remember to experiment with different kernels and hyperparameters to gain practical experience and to develop an intuition for how they work. Good luck.